Hey there. Today, we're going to explore this really beautiful, kind of quiet idea that's actually running behind the scenes of so much of our modern world, often without us even noticing. It's all about the simple art of finding the best way to get from one single place to everywhere else. It really all starts with a question you probably ask almost every day. You pull out your phone, you type in where you want to go, and boom, in a split second, you've got the fastest route. But have you ever wondered how it does that? How does it sift through what seems like an infinite number of possible turns and streets to find that one perfect path? Well, the secret, it lies in just shifting our perspective a little bit. Instead of seeing a big chaotic mess of roads and buildings, we can learn to see the world as something much simpler, much more elegant, just a network of connections.
And the main tool we use for this is something called a graph. Now, don't let the name intimidate you. It's a wonderfully simple concept. All it is a collection of points, which we call vertices, and the lines that connect them, which we call edges. That's it. Cities could be the points, and the roads connecting them could be the lines. Simple as that.
Okay, so let's just add one more little layer to this. In the real world, right, not all roads are the same. Some are longer, some have more traffic, some routes just take more time. We can show this by adding a number or a weight to each of those connecting lines. And just like that, we've created a weighted graph where every single path has a cost or a distance or some time attached to it.
So, think about a road trip, let's say from Chicago to Boston. That's a perfect way to see this. Every single intersection you might pass through becomes a point, a vertex. Every piece of road between them is a line, an edge. And the mileage of that road, well, that's its weight. And all of a sudden, this really complex map just turns into a puzzle that we can actually solve.
It's amazing, isn't it? With just that simple change in how we look at things, all that chaos starts to feel like something we can actually understand, something we can work with. So now that we have our map all laid out as this nice, neat, weighted graph, we can finally start asking the right kind of question to find the best way to get around.
And that question, well, it has a name. It's called the single source shortest path problem. It sounds a bit formal, but it really just means what it says. We pick one starting point, we'll call it our source, and our whole mission is to find the absolute shortest path from that one spot to every single other point on the map.
Now here's what's so cool about this. The goal isn't just to find the best way to get from point A to point B. It's bigger than that. It's about finding the best way from A to B, and from A to C, and from A to D. You get the idea. The solution literally builds a complete tree of the most efficient routes, all branching out from that one single starting point.
So it's not just about getting one answer. It's about creating this whole universe of solutions, all from a single origin. It's a much bigger and more complete picture than what we might have thought we were looking for. So how in the world do we actually solve this? Well, it's not with some big flash of genius. It's actually done with a very patient, very methodical process. So let's kind of peek under the hood and see how an algorithm thinks its way through the problem. Okay, so the most famous way to do this is with something called Dijkstra's algorithm, and it uses what's known as a greedy strategy. Now, that just means it doesn't try to solve the whole puzzle at once. Instead, at every single step, it makes the simplest, most obvious choice right in front of it. It always picks the next closest, or lightest, destination.
Let's walk through it together. We start at our source, that point labeled S. At this exact moment, that's the only place we know anything about. The distance to get there is, well, 0. Every other spot on the map, as far as we know, it's infinitely far away. It's just the unknown. So the algorithm does something really simple. It just looks at the immediate neighbors of S. It sees there's a path to point T with a cost of 10 and a path to point Y with a cost of 5. Well, since 5 is less than 10, it makes that greedy choice. It locks in the path to Y and says, okay, this is it. This is the shortest path to Y. And just like that, our little-known world has expanded by 1 point.
Now this is the really clever bit. Our known territory now includes both S and Y. So the algorithm looks at all the paths leading out from this whole area. It sees that old path from S to T that costs 10. But wait, there's a new path it can see now from our new known point Y to T, and that path only costs 3. So the total path from our start S through Y and then to T is 5 plus 3, which is 8. And since 8 is better than 10, the algorithm updates its map. It found a better way.
And that's really all it is. This patient process just repeats, over and over again. From its growing circle of known locations, it always just peeks out, finds the very next closest unknown spot, and updates its map if it finds a better route.
Step by patient step, it builds out that entire tree until every single destination has been reached in the absolute best way possible. So, this greedy approach, Dijkstra's algorithm, is incredibly fast and efficient, but it has one rule. All the distances, or weights, have to be positive. But what if a path could actually give you a gain instead of a cost, like a discount or a refund? For those kinds of maps with negative weights, we need a different tool, something like the Bellman-Ford algorithm. It's a bit more methodical, but it's built to handle those trickier situations.
It's just a really nice reminder, isn't it? That for every kind of puzzle out there, there's a special kind of key. Different problems sometimes just require different but often equally elegant ways to unlock them.
And the power of this idea, of seeing the world as a network and finding the most efficient path, well, it goes so much further than just our roadmaps.
I mean, this very same logic is what helps route data packets across the internet to bring you this right now. It helps design efficient phone networks. Airlines use it to figure out the most logical flight routes. It's even used in project management to find the one sequence of tasks that absolutely determines a project's timeline, what they call the critical path. It's everywhere.
So maybe the next time you pull out your map app and it instantly gives you the fastest way to get home, you can just take a second and appreciate that quiet, patient, really elegant process that's happening behind the screen. That step-by-step journey of always just finding the next closest thing.
And that kind of leaves us with a final thought, doesn't it? You have to wonder, what other complex journeys, maybe even in our own lives, could be simplified, maybe even made to feel beautiful, if we just stopped staring at that overwhelming, far-off destination, and instead just focused on finding the very next, closest step?